Hi. Yeah, we're gonna get started here in just a little bit. Just gonna hang out and see if anybody else joins in. I apologize. I do have a little company in doing this. Okay. So let's go ahead and get started here. It's a couple minutes after 4, so it'd be appropriate for us to go ahead and get started. Okay, so this is the review for AP Physics for simple harmonic motion. Basically, deal with periodic motion, simple harmonic motion, springs with a storing force, and ultimately waves as well. So there's a lot of different things that can be involved in this discussion, but it's really not all that bad. Just a little review of old material. Okay. First thing we wanted to go ahead and reference is the idea that what periodic motion is. Periodic motion is anything that undergoes a constant period. So that means that if something is going ahead and moving at some point in time, and as that happens, it does so in the same or replicable manner. So if it does undergo periodic motion, said to be an oscillator or an oscillatory system. If we have an oscillatory system where it does so and exhibits something in terms of a sine or cosine function, they're also said to be simple harmonic oscillators. In that these simple harmonic oscillators, they experience some type of restoring force. That restoring force is opposite in the direction in which it's moving at that point in time. So you can think about in terms of a spring or Hooke's law that the restoring force has that negative kx component. Okay, so that negative kx component means that it's negative in the direction in which it's moving, or in which it's examined in terms of its motion or oscillation. It's proportional to the distance it comes from equilibrium, not just that where it was originally. Basically, you have to think about it in terms of our equilibrium is now defined a new way when we look at an oscillator. It's no longer at a just fixed equilibrium point. Before we said it's just hanging out at that point. Now we're saying it's hanging out and then it gets stretched or pulled. So that new definition of X means not where it's at, but it means where it's and a mass is added and hangs down to that point. Okay. Hey, Sarah. With this idea, we can say that as this thing is stretched back from some point, its maximum point being pull back from there, it would be referenced as the amplitude. It's basically how it is from from some point. You can use amplitude as x maximum. We've kind of used that notation in class a little bit. And the period is the time for it to go from x max down to negative x max, then turn back to the positive x max. One common way I've seen people mess up is they've taken half the wavelength or half the period. It takes the full time for something to go ahead and move both down and back up, not just down. Okay, and relating the idea of a period and frequency, frequency is how fast oscillation is occurring, or basically how many wiggles per time interval. So what that means is in units of hertz, it's 1 wiggle per second if it was 1 hertz, and also hertz is order of 1 over seconds in terms of the units. In dealing with spring stuff, same thing, Hooke's law follows it in Stoop. Okay, first question we have here deals with indeed Hooke's law, and that's old ideas that kind of help us out. It says that ideal spring obeys Hooke's law, F equals negative kx. That just means that storing force is proportional to the distance from equilibrium. Okay, a mass of 0.5 kilograms hung vertically from the stretches the spring 0.075 meters. The value of the force constant of the spring is mostly these things. We're asked to find the value of force constant. To find the K is what we're looking for ultimately in this case. So what does that mean? We're thinking F is equal to negative Kx. So in this information, I apologize for my writing isn't that wonderful, but ultimately we have to go ahead and find the X component. Now we have X, how far it's moved from that original position, the 0.075, but we don't have F. Ultimately, that's the mass times G. It's the weight. So mg would be mg over x. In this case, would be equal to k. And if you plug and play with the numbers in which we have, the most appropriate answer you get for is E. Now, in this case, we notice that negative kx is there. We have to think to ourselves, okay, well, it gets pulled back, but the spring force constant is indeed a constant positive value. So that's what it's referencing. Okay, so that one's not really all that bad. You just have to think about Hooke's law a little bit. In looking at some old ideas, we also said that we can apply this idea. We did a little derivation in class to find the period of a spring. Oh, sorry, I messed up on that. Okay, we look at period of spring. It's 2 pi root m over k. I apologize, it doesn't look all that wonderful, but that's what indeed a period of a spring is. Potential energy of a spring is 1/2 kx squared. That's old stuff. And a pendulum can be thought of as an oscillator. The displacement needs to be small for it to work properly, and pendulum forces gravity and tension are those restoring forces. Period of a pendulum is 2 pi root L over G. Notice in both the period of pendulum and period of spring, we don't see an amplitude evident. And the weird thing is, a period of a pendulum, we don't see mass evident. It only appears in that period of a spring and that oscillator. Usually, I know I showed in class that it was a vertical spring oscillating. More appropriately, we can think about it as a horizontal spring oscillating. That's what you can really think about. Can you turn the audio off on the other one? So yeah, we're just saying that it's a horizontal oscillator. Okay. Now the other part that we want to deal with is ultimately dealing with the period. I got to tell you, we already did this problem in class just today. The length of period, simple period of Earth of 1 second is most near what? So we have to think that the period is equal to 2 pi, right? We're dealing with the period of a pendulum 2 pi root L over G. It's dependent all over the length and over G. That L is the length of the string, G is the gravitational constant. So if you were to think about this idea and just plug and chug, it's really not that bad to do. We find an answer. B is most appropriate in this case. If you were to be asked, okay, if you were to be asked to double the period, right, to double the period, that means that the length would have to be 4 times as great, because the square root of that ratio. If you were to say, okay, how can you double the frequency? 2 times F. Well, if you think about these ideas, twice the frequency means that it's 1/2 the period. Okay, so if you have twice the frequency is 1/2 the period, so you'd have to have a root 2 component in here. Okay. Okay. Some of these are pretty good. I like this next one. Okay. I did it again. I'm sorry, guys. Switch back to the pointer. Okay. An object swings on the end of a cord as a simple pendulum period t. Another object oscillates up and down at the end of a vertical spring, also with period t. If the masses of both objects have doubled, what is the new value of the period? So we said we've got a pendulum and we've got a spring. We have these two things and they're wiggling. What happens to the period if we double both those masses? Now, first thing you should think to yourself is it's set up to look kind of like a trick question because it kind of is a little bit. We should realize that with the pendulum, mass doesn't matter. So that is all garbage. That's all you need to think about. The only answer that will make sense now is B, because the period is not affected. Okay. But we do realize that those periods will be affected by the spring. If you think that it's root 2, why is that happening? Because it's 2 pi square root m over k. So if that's doubled, that means I'll have a root 2 out front of that. That's why that also makes sense. Okay. Okay. Continue on to the next one. Okay. Dealing with mechanical waves. A wave is a term that propagates through medium. Propagate just means a wiggle through medium. Medium means stuff that things go through with little or no net displacement of the particles of the medium. Parts of the wave, the crest is the high point, trough is low point, equilibrium is the midpoint, amplitude distance from equilibrium to crest, and the wavelength, the distance between those crests. Really, that's just the distance to when it repeats itself. Wave speed, the speed of a wave is a distance given a given point on a wave, such as a crest, given an interval. Velocity is distance over time, or velocity is equal to wavelength times frequency. Now, what we mean by that is just simple the wave equation to say that, okay, if I have that velocity, that thing is moving at a certain speed, that means that it's equal to the product of the frequency and the wavelength. Now, they do not change that velocity, but they do indeed change each other. The velocity of the wave is only dependent on the medium. Once again, the velocity of the wave is only dependent on the medium. We said the period of wave, one frequency, that's old stuff. Okay. Okay. We talked about different types of waves. A transverse wave is a wave in which the particle medium moves in direct and perpendicular. Okay. So if it's up and down and it moves that way, that's motion on the string. Longitudinal waves, also called compression waves, those move parallel or with it. Sound waves are a good one. We also said transverse waves, light or electromagnetic waves, and we see that electromagnetic waves are also here. Okay. This next problem deals with something we dealt with in class a little bit, and you have to think a little bit to show what's going on. A radar operates with a wavelength of 3 centimeters. The frequency of the wave is something. We've had a whole bunch of different things. You know, all we have here is the wavelength, but if you think V is equal to F lambda, okay, that is our wavelength. Okay, but you say to yourself, well, I'm asked to go ahead and find the frequency of these radio waves. I don't know V. Well, V is 3 times 10 to the 8th meters per second. Okay, I would give that to you to help you reference this. Okay, so that's the speed of the wave. Okay, that gives you the frequency. It's in 3 centimeters, so we need to recognize that we'd have to convert that to meters. Okay, and doing that and playing a little, with just, excuse me, with just a little bit of math, we find an answer of something like E. So really not that bad. The one little key there is knowing that that speed, again, I would not hide that from you. I would give that to you. Okay? Okay, so I want to erase that. And we're gonna keep going here. Okay. At any point in time, if you guys have a question, you can feel free to go ahead and type it in that chat in the side, and I'll try my best to kind of answer those. I can answer some at the end as well. Okay. Reflection of waves. Reflection is when a wave hits a boundary, then does something due to it. So reflection occurs when a wave strikes a medium boundary and bounces back from the original medium. We saw this. If it hits like this, things happen, right? Okay. So our question is one end of a pulse. Okay. Of a horizontal, whenever a horizontal string is fixed to a wall, A transverse wave pulse is generated at the other end, moves towards the wall as shown above, and is reflected at the wall. The properties of the reflected pulse include which of the following? It has a greater speed than the incident pulse. Incident means the thing coming in. Okay. It has a greater amplitude than the incident pulse. It is an opposite side. We should agree that the speed should not change. It's not going to a different medium. The amplitude should not change. We're not making it wiggle more. But it should get reflected. Yes, it is indeed just that last option 3. The amplitude should not be affected. Ultimately, the correct answer here is yes. It is B, 3 only. It's going to reflect on the opposite side. Okay. Dealing with superposition. This deals with reflection of wave and wave interference. When two or more waves pass a particular point under medium simultaneously, the resulting displacement at that point in the medium is the sum of displacements due to the individual waves. So what we're saying with that is, okay, is that they can go ahead and interfere with each other. Sometimes they can go and cancel out. Sometimes they can go ahead and add to make things greater. So those types of interference, if they are met in phase, it's called constructive. If they're met out of phase and partially annihilate, it's called destructive. The superposition, the interference, real waveforms may not appear to go the same way. They can go ahead and have different effects based on different frequencies. Okay. A standing wave is a wave that's reflected back and forth. Okay, so that makes some cool stuff, and that's where we see those node, anti-node things that we've seen previously. Okay. In this first multiple choice question that we have here, it's saying that we've got some different pulses. Okay, we're going to talk about standing waves a little bit more. Okay, so if we have two wave pulses, each of wavelength lambda, so the same wavelength, okay, they're traveling towards each other along the rope as shown. When both pulses are in the region between x and y, which are a distance lambda apart, the shape of which rope will most be the following. If you look at the wave on the left and you examine the wave on the right, examining both those two things, they're very, very similar. But the point we want to try to make is the fact that this one goes up and down, and the same amount as this one goes down and up. If we assume they have the same wavelength, when they meet, that up on the left, okay, and that down on the right, these 2 points are going to basically go ahead and cancel each other out, which means overall we'll have to have a cancellation. I know it's difficult to see this completely, but we're saying that they're coming towards each other like this and like this. They're both coming towards each other as this occurs. And we're saying that they're basically going to be at points x and y. They're both going to be occupying that same space. So as long as they have the same amplitudes, this way, we'll have a complete cancellation. That's one part that's not completely described here, but it is indeed true. Okay? And that shouldn't be all that bad as you see it. Again, with these wave questions that you like, these interference things, you have to say to yourself, what's really going on? How are they moving towards each other, and all that different stuff. That's one of those, things in which we definitely would go ahead and see the multiple choice type questions. Okay. 7 is another wave interference type problem. We got figures show two wave pulses that are coming towards each other. Okay. And as the one on the left is coming to the right, this one's coming to the left, and they're going to go ahead and we're going to have to see something occurring. We're going to see a partial annihilation, partial construction. If you look on this part here and this part here, they're both going up the same amount, so we expect to have something greater than we did originally. Well, all of those have something greater than we did originally, but that part over here on P and this part over here on Q are going to have a partial cancellation. How are they going to have a cancellation? It's not just going to be partial, it's going to be complete. This thing goes up just as much as that one goes down, so that will cancel out. That gives me correct answer of A. This chunk here will cancel out this chunk here, then this and this will indeed add. Okay? So correct answer is indeed A. Okay. Okay, so we take a look at this. A standing wave of a frequency 5 hertz is set up on a string 2 meters long with nodes at both ends in the center. The speed at which the wave propagates on the string is so much. You say, so, well, okay, what's going on here? You know, how can we figure this thing out? Well, we think of our wave equation, V is equal to F lambda. Okay. Now, with V is equal to F lambda, that means that we're trying to deal with both the frequency and the wavelength. Now, we have that frequency, 5 hertz, and we have, well, it says the string is 2 meters long, but we need to go ahead and think about this a little bit more. This, we have to look at it. Like, it starts here, right, and it goes through, and it comes back to the origin, and it goes up and comes back down again. Okay, cool. So it actually repeats itself one full time. So that means that this whole thing is not just, well, that whole thing itself is indeed the wavelength. Okay, that is indeed the wavelength. So that makes it kind of neat and interesting, but that is indeed the complete full wavelength. Cool. Okay. Now the second question, excuse me. So we're asked to find the velocity. If we think about it, the frequency is 5. If it's 2 meters long, well, that's not that tough to do. We're just multiplying those two things together, and we get d 5 meters per second. Not all that bad. Not all that bad. Okay, if we look at the next question, it's related to this one. Okay, it's the fundamental frequency of a vibration on a string is one of those things. Now, the fundamental means it's the first one in which we get a standing wave. So that means it doesn't look like this. It looks like this. So if you think about it, it's going to be wiggling half as much as it was to get this. So it was at 5. So the correct answer is B. That's the fundamental frequency, or the first harmonic. Basically, it will be second of, or it'll be 1/2 of the second harmonic. Okay, we'll talk about the standing waves quite a little bit more. Okay, and we move this up and over. Whoops, 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 whoops. Okay. Okay. Beats. Beats are the characteristics of loud, soft patterns when we have wave interference from 2 different sound waves. So that means if we have 2 sinusoidal functions of time are combined to obtain the result as shown in the figure above. Which of the following can best explain the use of that figure? Basically, you've got a whole bunch of random things that are written here. Beats are indeed the correct answer. Beats are this interference of what we're describing. Beats occur when we have these sound functions as they have different things going on. Okay? Next part, resonance. Resonance is a pretty neat and cool phenomenon. It occurs when vibrations from one oscillator occur at a natural frequency for another oscillator. And we get an increase in amplitude when this happens. Okay? And the first oscillator will cause the second thing to vibrate. We can make other things vibrate because of how things want to vibrate. We get an increase in amplitude. It's basically when someone's swinging on a swing, if we push them exactly at the right point, we get them to swing higher. We get an increase in amplitude. It's a pretty neat little phenomenon. Another idea that we're going to discuss here is the idea of Doppler effect. Doppler effect is the raising or lowering or the perceived pitch of a sound. It's why when an ambulance comes towards you, it's a high pitch, and when it goes away, it's low pitch. You actually have a compression of the sound waves, so you have an increase or decrease of the wavelength, so you have to proportionally change the frequency. So if something's coming towards you, the wavelength is shorter because you have a compression. What I'm referencing is the idea that if we have these sound waves coming out like this, okay, and they're coming towards you, or you're going towards it, you're going to go through these waves faster. That means that the wavelength would decrease. So that means that wavelength is going to decrease. Okay, so that means that frequency would have to increase. So that's why you hear when a car is coming towards you, wee, and when it's driving away, woo. Okay,
So in the Doppler effect for sound waves, factors that affect the frequency of the observer here include, which are the following: the speed of the source, speed of the observer, the loudness of the sound. Notice nowhere in here do we realize that amplitude affects this. Amplitude, once again, does not affect the frequency. The speed of the source would affect it. The speed of the observer would affect it. So yes, only those two. The amplitude does not matter at all. We get correct answer of C. Okay. And I believe we should have just one more here. And okay, this deals with Doppler effect that we just referenced. Okay. So a small vibrating object on the surface of a ripple tank is a source of a wave frequency of 20 hertz and a speed of 20 centimeters per second. If the source S is moving to the right, as shown above, the speed 20 centimeters at which the labeled points will be the frequency measured by a stationary observer will be the greatest where. So basically it's saying that we have something that's wiggling, right? And it's moving to the right, as shown, with a speed of that much, right? So we're asking ourselves, which of those points will the frequency be the greatest? That means would the wavelength be the smallest? So in looking at those things, you say to yourself, well, where does the space between the crests, where is that the smallest? When looking at those things, you can obviously see that there's distance between the crests with the smallest between C. That means it would have the greatest frequency. That's what we're describing there. Okay, so that kind of wraps up some of the ideas. We still have plenty of other things that we're not completely covered on this, but there are indeed some great ideas that were mentioned. What I'm going to do now is I'm actually going to go ahead and, excuse me, if you guys want, what I'm going to do is stop the recording.